Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, everyone. Welcome back to this afternoon's tutorial for the LATAMI Science Workshop. Prepare to have your socks knocked off because our next speaker is Drew Purvis, who's head of our Computational Ecology and I'm sorry, I just said that wrong, didn't I? Computational Environmental Science and Ecology Group in Microsoft Research Cambridge. Drew is becoming quite a superstar. In fact, he was recently on CNN in March, right? And then in January, he published his comments on ways in which we could model environmental science systems going forward from here, and it was a really fantastic article. So without further ado, I'd like to turn it over to Drew, and I promise I won't make you play the accordion.
Okay. So hi, everyone. Oh. So as Krista said, I'm Drew. Let me just go and look myself up on Bing, and I can remind myself who I am and what I do. We have, is that me there?
That's you.
Here we go, look. We can test the network connection too. I'm the head of this group here in Cambridge. And as you can see on this web page, if you take time to read it sometime, we're a group of ecologists, but we sit within Microsoft Research, which is a bit weird. And I never thought, as someone with a background in ecology, that I would end up working for Microsoft Research. But the group that we have that's why it's called the Computational Ecology Group. And we really do a very particular kind of ecology and environmental science that is aiming at trying to produce quantitative, predictive models of various aspects of the natural environment. And that's something that, by and large, ecology hasn't been able to do, and perhaps you could argue hasn't really tried to do very much. There have always been people interested in that, but by and large, we've tended to either look at some pure theory or look at some kind of relatively simple field work, or maybe some controlled experiments. And that's been fantastic, and ecology has a lovely, rich history. We've learned a lot about the natural world, but it hasn't enabled us to make the predictions that we need now to enable us to make a joined-up decision about how we manage our natural environment. And so our group is trying then is one of several groups around the world focusing on that kind of quantitative predictive modeling. I think what makes our group a little bit different, though, is we have an explicit goal of also producing software which will enable a much wider group of scientists to become involved in that kind of work. So to be able to build these sorts of predictive models, to be able to share those models with others and modify them and extend them and combine them in different ways. That's what we think of as open modeling. You hear about open data, but we're thinking there about open modeling. And then finally share those model predictions with important decision makers, like governmental decision makers, people that work for NGOs, businesses, and citizens, and so on. So the tutorial this afternoon is, these are all early prototypes. These are certainly not, kind of finished articles, and we're very interested in anyone that might want to work with us to provide feedback about these tools. As we say in Britain, do you have the phrase having a thick skin? I don't know if you guys have that in Latin America, but it means I won't be offended if you insult the tool. So I'd be very, very interested in feedback, positive or negative, on these tools. And if anyone wants to try using them, you could become a kind of beta tester, if you like, for these tools. Just let us know. Some of them are already open, and those that aren't will be soon. And we're just very interested in working with everyone. So that's what this is about. So today, we're actually going to we're going to use some of these tools together. You're going to be breaking into groups, and we're going to give that a go. And if everything's successful, by the end of the day, together in this room, we will have created a set of, I think, 10 new models predicting fire, natural primary productivity, that's the rate that carbon goes into trees, and the yield of 10 different crops. And we're going to create those models together, train them using Bayesian inference to estimate the parameters, and then we're going to upload those models into a web service that means that anyone in the world with an HTML5 compliant browser can actually go and run those models on demand at any scale, anywhere in the world, for the past or into the future. Okay? But of course it might not work, so we'll see. But that's the idea. So I know it's just after lunch, so I thought what I'll quickly do is take you to one of these tools. It's the first one we're going to use today. FetchClimate, it's called. And here it is. And if anyone wants to get there, you can try fetch. So did you see that URL? Let me try that again, because it kind of gets longer when you do it. So it's fetchclimate2.cloudapp.net. So anyone with a laptop, and I hope you've got an HTML5 compliant browser. That means just a recent browser of any kind. You can go and try that one out and have a look. And then we're going to be using a slightly different one in a minute. So the one we're going to be using is actually even shorter, aka.ms/fc2. And so if we go to aka.ms/fc2, it's much easier to type than say, right? Then we'll see something like this. But what I'm going to do is I'm just going to click on where here. This is a little... This is where you choose on the map. And we're going to do this, don't worry, in the next hour if you're not keeping up right now. Because as you'll see, I've got a really trivial reason for doing this right now. Because this, my understanding, is Latin America, roughly, right? Right here. It starts with Mexico and goes all the way down, right? And most of the people here are from Latin America, is that right? Must be right. So what I thought I would do is, I'm going to hover the mouse over the map, and when your country, when the pointer's hovering over your country, I want you to shout out and go, yay, or... Okay, all right, so we'll give that a go. I thought I'd wait you up, and then it'll give me an idea about the geographical distribution of my audience. Okay, so here we go. No one from Mexico. Does Mexico count as Latin America? It does, right? But no one from Mexico. Is there? Oh, come on, we need a shout. All right, cool. All right, so that's right. All right, let's go down now. Whoa, here we go. I won't take too long over this, but here we go. Oh, wow, we're definitely missing some whole countries by the looks of it. No Colombians either. Hey, all right, great, good. Venezuelans? Ecuadorians? Excellent. Oh, good. Jame's a colleague of mine, so there we go. Peruvians? Well done. All right, here we go. And there's this really big country here. All right, good. Excellent. And here we go. Since we've already been at this quite a long time, let's try the rest of them really quickly. Ready? Here we go. Okay, right. I hope you'll manage to get it there. There we go. I was hoping you might cheer a bit louder, but hopefully by the end of the it is just after lunch. But hopefully by the end of the session, you'll have your cheering head on, okay? So this thing here, FetchClimate 2, as it's called, because it's an upgrade of the one that we launched a year ago, is one of our tools. And I'm just going to zoom back in a little bit. That's a bit too far out, even for me. And what you can see here, it enables someone to go, and this is what you can fetch, okay? And so, for example, we could go and get bird species richness, or we can get things like elevation above sea level, or the predicted mean carbon storage. Some of these things, the ones I've just fetched aren't, but some of them are indexed by time. So this one isn't, so we won't index it by day or time. You go and pick a region on the world somewhere. So I'm going to put a little thing here. And we go and hit fetch. And what's happening here is this HTML5 front end is communicating with a back end that is running on Azure. And it's looking at our query. It's choosing the appropriate data set. It's subsetting, regridding, doing the calculations, the interpolation, and so on. And it's sending the results back to the browser, and we're then viewing them in the browser. Okay? And so we can see here that south of the Amazon River, we tend to see a much higher bird diversity, about 600 species we think could potentially live in that region, 600 different bird species. But north of the Amazon River there, it's much less, about half as much. And that's because the Amazon River is such a big river that it's actually the northern boundary of lots of different bird species. It's the northern edge. They don't extend beyond the Amazon. Okay? And we can look at predicted carbon here. So this is the predicted amount of carbon that's held in the trees in those different areas. And we can see it's 17 kilograms per kilometer squared here. Ignore those units. It's definitely more than 17 kilograms per kilometer squared. I'm going to have to talk to my colleagues about those units, but that's fine. I'm sure in relative term it's fine, and it's much lower here. Okay, so the green to brown is the idea. So this is one of our tools, and we're going to spend the first bit of our session. I'm going to go through this again more slowly. I'm going to tell you about some of the different fetches that you can do and how to do them, and then we're going to break up into groups, and we've got some questions here on these bits of paper that we printed off earlier, and you're going to use FetchClimate to have a stab at answering these questions. And then at the end of the tutorial, you're going to report back to the rest of the room your answer, okay, that you got using FetchClimate. That's the idea. So I'm going to have another maybe 10 minutes, 15 minutes maybe, using FetchClimate in front of you. So that's the kind of lecture-y style bit over, and then we're going to break up into groups and so on. So here we go. So let's go back to so again, you know, obviously there are several ways to use FetchClimate. This is the kind of the most visual, kind of friendly way. This is the UI way, but there's also a text request kind of form that you can fill in, and that enables you to do some more precise kinds of fetches. Like if you had an exact list of coordinates and times, you could do that using the text form. So, but let's just stick with and also we have an Excel add-in, which I can show anyone if they're interested. And so you can, if you've got a list of lat long positions in Excel, you can also hook out information using the Excel add-in. And then we're working on having FetchClimate from R. So there is an API and a REST interface. So in principle, you should be able to get to this tool from many different places. And you can get to it from inside any .NET program already. So here we are. So this bit's the easy bit. You go and choose your variable, and you can see the description of the variable here in bold. And underneath, there's a list of data sets that can potentially fulfill that query for that variable. So this is important with FetchClimate, that you don't go in looking for a data set. But most of the open data initiatives that we see, you go in looking for a data set. Here you go and you ask for the information that you want. And that information can potentially be served by many different data sets. So one example here is the air temperature near the surface. And you can see that there are no less than 5 different data sets already in there that can potentially fulfill a query about air temperature. So for example, the GFDL data set is actually a set of predictions about the future. Whereas the NCEP NCAR reanalysis is a data set that pertains to the past. And the CRU data set is what's called a climatology data set. So that gives you an average condition over a grid. So these were originally designed to fulfill different purposes. But what FetchClimate is going to do is, given the details of your query, it's going to choose the right data. And if necessary, stitch them together. So if you do a query from the past into the future, it will actually stitch together data sets as necessary to give you a single time series of air temperature. So let's do air temperature, why not? So the simplest thing we could do is say, so we have to pick, so then we go to, so that's what, now we go to when. And we can pick a range of years. So to start very, very simple, we could do 2012 to 2012. And it says over that range of years, do we want a value for each individual year? Now 2012 to 2012, just 1 year, but maybe, tell you what, let's illustrate that by at least starting off with a different one. So here, 2012 to 2022. And what it's saying is, do we want to take that period and average over that whole period to give us the average? Or do we want to split it by individual years? And now we're going to get a time series stepping forward in at 10 years at a time. Or if we want, we can actually average over chunks of, say, 2 years each. And that way we'll get an average for the first 2 years, followed by an average for the second 2 years. Does that make sense? I know there's some computer scientists in the audience. It's not difficult stuff, right? But that's the point. It's supposed to be easy. Now, similarly, we can index also by day of the year and hour of the day. So if we wanted, for example, to do a typical seasonality of temperature in a place, then we could choose this one, which is 12 monthly averages. And now we'll get for that range for each of those pairs, we will get 12 values. Does that make sense? So we'll get 12 values for the first pair, 12 values for the second pair. But if we average over the whole period, we're going to get 12 values which represent an average over that whole time. And then similarly with hours of the day. So if we average over the whole day, we'll get what I just described. But if, for instance, we do individual hours, we'll now get for that period, and for each month, we're going to get 24 values. So we'll get 24 values for January, which represents the typical daily cycle in January. And we'll get 24 values for February, representing a typical daily pattern in February. So I think of time as an ecologist as a three-dimensional object. We're trained to think of it as a one-dimensional line that we split up, but really because nature, well, at least the Earth, has these two dominant cyclicities: the diurnal cycle, which is obviously the Earth rotating, and the annual cycle, the Earth going around the sun. So it makes sense to think of 3D time. Does that make sense? Three-dimensional time. Years, day of the year, and hours of the day. And we can average over that in different directions, as I'll illustrate in a second. But if we do an average over the whole day, and an average over the whole year, and an average over the whole period, we're just going to get one number. Okay? But then there's where to think about. And so here we can either do a point. So the very, very simplest thing we can do is a point. And now we really are just going to get one number for that point. However, in addition, or instead of, we can add an area. And now the when that we just did will apply to each grid cell in that box. And we can cut up the box how we want. By default, it's 30 by 30, but we can do 100 by 100 or 200 by 200 or what have you. So for each of the cells in this grid, we're going to get one value, because that's what we specified up there. So let's finally do the fetch then. I know that was a bit slow, but I just wanted to step through it. Now I'll step through some a little bit faster. So this thing's then going off, and it's actually running the query against multiple data sets, is how it works. And it calculates the uncertainty, so you get the uncertainty on the fetch back as well when you use FetchClimate. And by default, it returns the answer that has the lowest average uncertainty. Okay? But you can override that with the text form, as you'll see later, if you're interested in particular data sets. So now we can hover over, and we can see that for the time period that we defined in when, and given that this is air temperature near the surface, we can hover over here and have a look at the answer. And we can see it's 27.5 over there, and a little bit less over there, 24.2. Simple stuff, right? But if we go and kill those regions, now let's say we add a point just here instead. Now we can go and do something more sophisticated in time, and let's say, well, let's look at individual years then for that period. So again, averaging over the whole year and the whole of the day, but now indexing year to year. And now we're going to get air temperature. We're expecting to get air temperature for each of these years. And can you see there's a control now that's appeared on the UI there? And anyone feel free to keep up with this, by the way, as much as you want. It is open. So, and now you can see as we step through, we can see this time series up here for the time that we asked. Does that make sense? And if we go back, and we can add more points if we like. And obviously doing that by hand is not necessarily very useful, but as I mentioned in the text form, you can actually paste in a list of lat-long values. So if you did have, for example, flux tower sites or places where you placed environmental sensors or anything at all, you'd be able to paste that into the form, and now you would have that time series for each of those points. And as you hover over here, you'll see the one that you're hovering over is highlighted. You see that? You can step through. So that's an example for each of those places of pulling out a year-by-year time series. But now we can average over time in a different way by saying, well, let's average over the period, let's say, 1990 to 2000. So now we're going to average over the years, but divide according to the months for that same list of points. And so it's the same data, but we're looking at it, I think, in a different dimension. And so now the time index has changed into 12 months. You can see that, right? And so for each of these places, we now get a time series that represents not the change year to year, but a typical seasonal pattern. Or actually, it's not a typical seasonal pattern. It's actually an actual seasonal pattern for each of those places. Can you see that? So it's saying over that period of 10 years, that was the typical annual cycle of temperature at that point, and that was the typical annual cycle of temperature at a different point. So let's go and clear our fetches now. Now we can also do a grid by time. So we can say, and these take a bit longer. So you'd have to be a little bit patient sometimes because the fetches can take a bit of time. There's actually quite a lot going on in the background. So here we can say now, let's look at individual years again, say from 2000 to 2030 for that grid. And now what we're going to see again, now we've got our yearly index up there, and now we're going to see how that map has changed in the past, from 2000 up to about 2010, after which FetchClimate is going to use one of the historical data sets to fulfill this part of the query, and it's then going to switch into using the GFDL predictions. Okay. And so we can see how not only how the map of temperature across that region has changed in the past, but then we can see, according to this model prediction, how it might potentially change in the future. That makes sense. And these fetches this is a variable one, so as in sometimes these fetches take a shorter amount of time and sometimes they take a bit longer. This one usually takes a bit less than a minute, okay? But occasionally it takes sort of 3. So it's one of those tricky things because we specifically built FetchClimate because in the work we were doing, we needed this kind of information all the time, and it took just ages and ages to get that information. Whereas now it might take 1, 2, 3 minutes. But unfortunately for a demo, it's a really bad demo, right? 1, 2, 3 minutes. So it's, oh, hey, here we go. All right. And so you can see here as we go from, there's not much going on the map there. Now, there is an issue here. I noticed this, that something funny happens here when it's stitching the data sets together. There's some funny stitching. So they're looking into that. So I told you this is a prototype, right? But you can see then we can hover over and, according to the model, the region is projected to warm to a certain extent. Okay, you see that here. Now, for any of the fetches, we can download the data. So we can do that by clicking this button here. And we get a cloud of points here. And we can just copy that and paste it into Excel, for example. I know that's a bit simplistic, but it's just to keep it as simple as possible. Oh, it pasted in a picture of my desktop instead. Okay, I'm going to try that again. I didn't expect that. Okay, let's try that again. There we are. Amazing. Oh, well. Moving on. Okay, I don't know what happened there. I tried it in my hotel room and back in my office, I promise. There's something funny going on with the way that's very funny. All right, so I guess that's going to limit us a little bit at some point. I mean, most of the time you can look at, you'll see later we can use this text request form, by the way, to do these. So I'm just wondering if there's anything else in terms of the nature of the fetch that you really need to understand, but I don't think so. You can obviously practice in a bit when we get to these questions. So, but the idea is you can combine any combination of the variables with the indexing by year or averaging over years with the months or particular period. You can do weeks if you want. So notice here that the 12-month average is only one option. You could do an average for part of the year. So you could say do 120 to 180. And then this will give you an average only for May and June. So that way you could do, for instance, a year-to-year time series of June temperature, if that makes sense. Or you could even have a particular day if you want. So you could look at how the temperature on your birthday has varied for the last 30 years and might change into the future. And you can do the averaging over chunks. So you could say 1 to 365 in chunks of 7. And then that is going to give you a weekly index. Okay. So you can combine the temporal fetching with as many different grids as you want, placed anywhere, and any combination of points. It doesn't have to be one or the other. And then you can fetch multiple things at once as well. So there's, if you want to. Notice if you do, in this case, we indexed it by year and we indexed it by day of the year. So now we'll get a double thing here, and you can actually navigate back and forth. And there's probably so the final little thing I'd probably say about the UI is that you can, all the information about the fetch is in the URL. So if you copy that and put it in an email to someone else, then all they need to do is click on that link and they'll get back to exactly this. The fetch will happen again. And so that means that, if you wanted to say, as we'll see in one of the questions, you're advising your sister on where she should get married or when she should get married, then you'll be able to just paste it into an email and say, trust me, you don't want to be getting married in Colombia in the wet season or whatever it might be. So that's kind of the UI bit. Any questions straight away? Because I don't want to go racing ahead. Okay, yeah, please.
I work a lot with data series, one of the things that I've seen is that the manner in which you model time series, the way I model the data series in a database really affect the output throughput time. So, for instance, if I model it as a sequential form, the query takes 3 minutes. If I model it in some other form, it takes 8 hours. So, was there some kind of special modeling in order to extract the data so fast from your database?
I mean, the short answer is yes. So that the performance has been a real issue, and there's lots of clever stuff going on in the background to make it faster. Actually, so that's a nice chance to be able to acknowledge a university group that we work with on this. That's a group at Moscow State University. Very, very clever PhD students and a professor and others there, and who've actually built all of this stuff. And yeah, there is quite a lot going on in the back end. So. One thing that's easy to describe which is really good for your sharing the URL or for repeating bits of science, is that there's local, that is client, and server-side caching of all queries. So that if you run a query where exactly that query has been run before, it'd be very, very fast because it simply gives you the same answer back, which can be really nice actually for sharing, for sharing these with other people. Otherwise, there's basically a lot going on in terms of, even things like the data is compressed as needed and so on, and they don't necessarily look at all the smaller decimal points at certain parts of the calculation, and lots of things. Yeah, so.
I imagine. And the second question is, one of the operations I do frequently is a moving average. Instead of, getting the measure of every week, I want the average of the last 7 days.
Yeah.
And that's a very hard operation to do.
It is, yeah. So you can't do that at the moment in the UIs that we have. So you can't do it in the Excel add-in, in the UI that I've just shown you, or the text form. But because there is a REST interface, you can do it yourself, because you can fire off lots of individual queries. And so you could just say, give me exactly this. Having said that, I think that moving windows are something that we should perhaps think about as a standard thing anyway, because it's quite a reasonable thing to want. Yeah, it's quite interesting. And for various ecological processes, you even a moving window, you might want, like you said, the 10 days running up to a time. So like if you're thinking of fire, the chance of fire on a particular day is probably a function of things like the rainfall over the last 2 months up to that day, right? Yeah. So they're both good questions. Thanks.
Thank you very much.
You're very welcome. So honestly, I'm not going to hang around too much longer doing lectures, because I think you're going to get to use this. But just to let you know that here's the text request form here. Okay, it's just down there, and if you click on that, you'll get something like this. And so you can choose which variables, just like before, but you can actually choose which data sets you want to potentially fulfill the query. And then here you can choose all of the information that you just saw in terms of years, days within the year, and hours within the day. But then down here, you can paste in a list of lat-long positions. So if you had a file somewhere else where you've got a list of lat-long, or you can define a precise grid, so you don't have to click with your fingers. And then you can download the results. And that does work. I've tried that one. And then while we're in the groups, I will see if I can work out that copy and paste thing, because it should be very simple. You saw me copy that list of numbers and paste them into Excel. So maybe we'll try it in the old version of Excel. Maybe that'll work. So this is where the group bit begins, right? I wasn't joking about splitting into groups. So we've got 13 different questions. And what I would like is, therefore, for you to break into 13 different groups. And each group has to have a laptop that has wireless access. And then you've got to come up and grab one question. And then I'm going to give you about 20 minutes to have a go at answering the question. And then we're going to take it in turns answering back. And we decided to trust in your ability to self-assemble. So rather than try it, so I'm just going to trust that you're able to break into 13 groups just like that. So how long do you want to do it? Come on, up you get. And you need to, I figured if you turn around some chairs like this, you can you can make little groups of 6 people looking at each other, or 10 people, or whatever it is. So, all right, everyone. I think we'll reconvene. And yeah, sure. Just here. Now, this tutorial was always going to be a 2-way learning experience. So I've definitely learned some things about the fact that we need a bit more space on Azure if we're going to do these things again, and so on. So I think there was a common problem across the different groups, which is that some of the fetches are taking a very long time. Is that right? So a lot of people were looking at this. So I'm sorry about that. All right, is everyone ready to settle down and report back, that kind of thing? All right, everyone, so it's 3 o'clock. Now, so as I mentioned, we are interested in feedback about FetchClimate. So, and if the feedback is the fetches take a really long time, that's fine, you see. If I have a collection of feedback like that, then I can go and lobby someone for more space on Azure to make the fetches faster. So what I thought we'd do is we'll take it in turns to report back. So we do have someone with a handheld mic. We've got a handheld mic in the room, right? Okay, cool. So I've got the questions up here. Now I realized that because some of the fetches were taking a long time, I think most of what I saw, it looked like people had got it right, which is great news. And unfortunately, some of the fetches were taking a long time. So some people weren't able to get to the answer they should have been able to get to for that reason. So I'm sorry about that. So I realized that some people may not feel they have answers to these questions, and that's okay. But hopefully we'll get more than, well, one or more groups that feel that they did get some kind of answer to the question. And because I don't know where in the room the questions are, so, oh, okay, great. So I'm going to call out the question, and then the group that had that, if you guys shout, and the mic will come over to you, and then just give us a really, really brief summary. And then, as I said, ideally, if you do feel you're able to get an answer, do email me the URL, because what I'm going to do is I'm going to collect all that together, and I'm going to email all of you guys. So it's not for me, really. It's for all of you. So then you can see how the other groups, the URLs they used to look at the fetch, okay? And even if some of those didn't work, because they took forever, hopefully when we all go back and we're not all using it at the same time, because it is just one service on Azure, those fetches will work, okay? So here we go. So who had, how has rainfall been changing in Paraguay? Come on, you guys. It depends on your shout. So who wants to report back? Okay, so the answer is you don't know because it's too slow. All right, that's okay. That's not your fault. So what about describe and illustrate the pattern of sea depth in the Caribbean Sea? Who had that one? Cool. And did you email me the URL yet, Gemma? Okay, good, okay.
So we were able to compare the whole pattern, but not to take the average in a single block. Oh, okay.
Now you go ahead. You talk. And
we just selected the two regions with the selection mode, and then we looked for bathymetry. And just fetch the bathymetry.
Were you using the old version of FetchClimate, Gianmarco? I think you probably were. I forgot to tell you, there is an old version that is working.
Yeah,
so it's fine. For that question, the old version works just fine.
Working
so we'll
fine,
see that.
yeah.
But it is a Silverlight app, so it's going to have to download.
Okay.
You know, I hope you realize, one day you might be on the other side of the podium. These things are kind of a high-risk activity, right? They are. So there's always a good chance if you give a tutorial, you'll fall flat on your face in one of several different ways. And so here we go. So this was the fetch that Gianmarco did in the old FetchClimate, but you could do the same fetch in the new one, and you get a very similar answer. So here's the Caribbean, and And so Gianmarco was able to send me that URL. I've clicked on it, and now we can hover over here and have a look at how sea depth varies around the Caribbean, right, Gianmarco? And then we can go over here and compare that with the
How can you
Caribbean.
take the average of a single block? Is it possible to do that? The average
it is in FetchClimate 2.
Okay,
Yeah.
not in this version.
So like if we did that here. C2. No, it isn't. I lie. I don't think we have made it possible to do an average over a whole region like that. And if that's something interesting, yeah. I mean, so I guess you'd have to do it the hard way right now. That you download that grid, and you would take an average offline. But that's we ought to do that. It's a perfectly reasonable thing to want to do, actually. So yeah, we only support points or grids, but we don't support regions. So that was just a choice you made on the UI. Okay, let's have a look at some of the other questions. We'll just zip through them. And as I said, it's fine if you didn't manage to get there because it was too slow. That's not your fault. Who have which major city in South America has the greatest seasonality and temperature? Anyone? All right, we're going to move on. Someone had it, I thought. Okay. Your sister's getting married on May the 15th next year. Who had that one? Okay, you guys. It's just here. And did you manage to get through that? Yeah? All right, cool. Well, let's hear what you would advise your sister. And did you manage to email me the URL at all? Cool. Let's have a look.
Oh, it's on. Yeah, so we decided that central Brazil was a good place to have the wedding. We tried to drill down.
Is this you?
Further. No, my name's Mark.
Oh, boy. I hope you didn't get put into junk. That would be really mean. Oh, you did. That's not me, right? Okay. Not junk. Oh, look at that. I'm going to have to copy this manually. There we go. And as I said, it does...
so we started with
yeah,
a large area. We tried to drill down to a smaller area, but the queries took a very long time.
Cool.
Try streaming.
So you looked at air temperature, precip, and relative humidity, right? Makes sense. And you can see roughly, based on that idea, and actually you can see the ocean there as well, right? You'd be able to give your sister some advice about, given that she was... So does everyone understand there that this is... although it's another average, it's an average for just a particular time of year, right? I think May the 15th or whatever, okay? So you can say, what does a typical May 15th look like over that map? And obviously, your sister's wedding is a kind of trivial example for environmental science, but it's a similar kind of fetch that you would do for other things. So. All right, well done, thanks. We've got, you are tasked with placing a wind farm in Brazil. Who got the wind farm? We're going to need some hands up, you guys. It's who got the wind farm? Okay, no wind farm. Thanks. Cheers. Where are you guys? Come on, hands up, shouting. Thanks, dudes. Thank you. All right, cool.
We couldn't.
Because the fetches were too slow, were they? Or?
No, we found some places outside of Brazil and couldn't just narrow down to one that was inside the country.
Okay, cool.
Yeah, the square was, we couldn't select only the Brazil area.
All right, fair enough. And did you, so, well, we can maybe talk about that after a little while, but obviously the idea would be that we talked about, I mentioned in my keynote about decision making, and the idea is that looking across a set of these variables so for wind speed, obviously the average wind speed and the seasonality of wind speed, then you'd be able to make some kind of informed decision about where to put a wind farm. That was the idea. So thanks for trying, and we could talk about it a little bit later. There was a similar one about solar energy. Did anyone have a go at the solar plant? No solar panels. All right, what about the bird reserve? Anyone do the bird reserve? Okay, all right. Fetch is taking too long. Yeah, okay, all right, fair enough. Well, I'll tell you what we'll do. I think, did you guys get anywhere with the MPP one? All right, cool, thank you. So let's have a look at this. And what's your name, sorry? There we are, great. So these guys were tasked with looking at how NPP is the net primary productivity. It's the rate that carbon goes into vegetation. And that was actually something that wasn't in the FetchClimate originally, so I put it in there why these after a couple of minutes. And these guys were tasked with looking at the ratio of the two, right? So did you find anything out? There we go.
Sorry, yes.
All right. Well, I think we will move. I don't think we're going to carry this exercise on too much longer. But I certainly get the idea, right? Does anyone else feel that they had a question that they did get an answer to and they'd like to volunteer rather than me going through them? Anyone fancy reporting back? Or do you think we should move on?
Well, by looking at the map itself, we had the frost question. We decided that frost is the question on the over there. Okay, yes. Which areas in Latin America never experienced frost? We decided that there were the green areas from this, and the white areas have some frost, and lower latitudes get more frost. And if you're near the sea, you also seem to have a little bit more frost also.
Okay, all right. But you didn't actually manage to get, unfortunately, again, you found that the fetch was too slow in your
Yes, but I sent you an email with the fetch as well.
All right, guys, so let's just change gear slightly then. And I'll say, from the heart, thanks very much for trying. And it sounds like 99% of the problems were on our end, not on yours, as I expected. So it's definitely been a learning curve for us. I hope that you'll be enthusiastic about trying this offline, because I do think that the slow fetches, even if it takes 10 or 15 minutes to do a fetch, so some of the large fetches do, because if you do, say, a grid by time for a lot of points, obviously that will take quite a while. I think we experienced a lot more problems here because we're all hitting the service at once, and it does only run on a certain fraction of Azure. So I hope you'll be keen to at least try using it in your own research at some point. And again, very, very keen on hearing your feedback, so anytime you want to get in touch, okay? So I really appreciate you trying and being up for it, so to speak. And then just as a reminder, there are other ways to use FetchClimate. So you can use it directly from a .NET program. Some of you tried using the text request form down here. You can, and then also watch this space, because we will be releasing details about how to use FetchClimate from R, for example, and possibly from things like MATLAB as well. And we may also be open sourcing important aspects of FetchClimate. So if you fancy actually getting your hands dirty and modifying it, that would be great too. So that was kind of the first phase of the 3 bits of the tutorial this afternoon, the FetchClimate bit. And we're at 3:15 now. We're going to finish at 4 o'clock, okay? And the second part of this part of the tutorial, which finishes at 4, is going to be about, we're going to shift gear a little bit, and it's going to be mostly about the concepts, about how we go about fitting complex models to data. So it's a very different sort of activity. Okay, so we're going to change gear a little bit. And so, don't you remember when I was talking at the start about this, to make it easier for people to build models and then train those models and then share those models with others, right? So we've got this sort of 3-way activity. And the FetchClimate is about saying, the typical way you would do that is you would have some private data, some data of your own about something that matters, and you could supplement that with FetchClimate. So you would then have the 2 things sitting next to each other. And then you can go and define some model that relates the two, relates the environmental predictors to the thing that you care about. And you want to then train that model against the data, as we say, right? That then means we can then reapply that model to make predictions somewhere new, like a new part of the world, or predictions into the future, and so on. Now, in the middle of that is this idea, though, that, of course, you can define the model that you want and fit it to data. And that simple idea is very easy to say, but traditionally it's been very hard to do. So I just want to go through, and this is kind of more of a kind of lecture style bit here, mostly. Because there's been kind of a revolution in the way we do that now in environmental science over the last few years. I know many people in the room would be well aware of this, but which has been enabled by the use of Bayesian statistics. And they're typically very heavy on the computational side, but as computers have got faster, and then we've learned how to use that fast computation, we're now able to train much more interesting, process-rich models against the data in a way that was kind of unthinkable before. So by way of a background, we can think about when I, let's say, was at university doing ecology, which was, by my standards, wasn't all that long ago, like mid-90s. The way we were sort of taught to think about answering a question in ecology, to the extent, and then to talk about a question that is informed by a model here, was that you would think about your model. So here's and a model here is, like a model always is, a set of ideas about how the world works, encoded in some mathematics, some equations. So let's say, in ecology we'd have things like the Lotka-Volterra model, and I know there are lots of people here that do different subjects, but there would be this common idea of a model of the processes involved. But and of course you could play with the model by itself, and that can be great fun. That's theoretical ecology, right? So you just play with it and you're able to say, well, if this, then that. And that's kind of interesting perhaps for helping your thinking. But if you really want to tie it down to reality, there's going to be data involved. So how is the data used in conjunction with the model, traditionally? And this is traditional kind of hypothesis-driven science. And so here's your data here, let's say. So you've got your model and your data. Well, how was it done? Well, what you would really do is you take your model and you would boil it down to some qualitative prediction, often. So it might say something like, well, according to my model of leaves, there should be more evergreen leaves where it's cold, or whatever it might be. So here's it would be qualitative. Okay? And you would take your data and you put it through a predefined statistical routine. Okay? These are stats, if you like. And those stats would give you some kind of metric, like an F value or the p-value from a t-test or something like this. And you would then compare this metric with your qualitative prediction. And you'd obviously use your brain, right? I mean, and it's not that we didn't learn anything doing this. We learned a lot. So you'd have to choose the right statistical test and look at the right metric in the right way so that it gave you a kind of yes-no answer, basically, to your qualitative prediction. That's the traditional way that you would use sort of model and theory in conjunction with data to try and understand the world better. Whereas, but what if you wanted to actually make a quantitative prediction about anything? This really doesn't give you that at all. And that's because the model that's being used here is not the model that you actually think represents how the world works. It's a different model. This model was designed by an ecologist. This model was designed by a statistician. So obviously, there's a quite different activity which would use, again, traditionally, a different suite of predefined statistical models to look for relationships in data, kind of regression-like modeling, to make predictions. And that can give you predictions. And in fact, in the last section of the day, we'll actually be using models that are really kind of in that direction. They're sort of not very rich in terms of the processes about the reality that's going on. They're just something like a regression. They're just a set of relationships. So they still have their role. But once again, though, the model that you're using to predict, then, in that case, has not been designed by an ecologist that knows anything about the way the actual system works, or a physiologist, or a climate model, or anything. It's been designed by a statistician. And the reason that statisticians design these models is because they needed to be able to train the model. So when you run a traditional statistical routine, like a linear regression, or a t-test, or an ANOVA, you're actually parameterizing, training a model against the data. You don't usually verbalize it that way, because as scientists, we don't want to confuse it with this kind of model. But that's actually what's happening. And those models that are used in those predefined statistical routines have been chosen because they could be trained against the data very quickly without lots of computation. There were analytical ways to jump to the correct answer trained against the data. Okay? So they've been chosen for kind of computational convenience, not because we actually think they're a good representation of the real world. Now, when does that matter and when does that not matter? Well, that approach can be okay for interpolation. So as an example, let's imagine that I gave you a time series like this, time, and I gave you some points. So that's what you've got. And so the traditional approach could say, well, that's okay. I can fit a straight line to this, let's say, approximately, a linear regression. And that way, so what's good and bad about that approach? Well, that's a pretty good approach if you want to interpolate. If you want to know what the data was in between when it was observed, you can see that's pretty good. Who really cares what the model is, as long as it seems to go through the points fairly well when you're interpolating? But if I told you that, under prediction, however, you can see that you go zooming out. Now, if you do it properly, of course, when you do your linear regression, you should see something that's kind of like this when you do your prediction. Okay. So, to be fair, it should tell you that there's a huge amount of uncertainty, because it should say, as you extrapolate from the data, but it's not very useful prediction. But if I told you that those points were the position of a rubber ball measured through time, then of course, instead of using some predefined statistical routine, you'd prefer to use something like Newton's equations of motion that describe bodies moving in space. And then you might be able to then make a prediction that looks something like this. The difference is then that you're able to extrapolate with some confidence because you replaced your statistical model with a process-based model that actually represents how you think the real system works. And the reason then you don't necessarily get this huge fan out of uncertainty, now actually you kind of do later on, we could talk about that later, but over this, say, range here, is because you've constrained the possible futures by loading in the knowledge that's in your brain about how the real system works. So you didn't have to just rely purely on the data anymore, because you've actually got a scientific understanding about how a rubber ball behaves. So the idea is, what we'd like to do then, to make predictions, and almost all the interesting environmental science is about extrapolation. It's about predicting what's going to happen in a world of higher CO2, of unprecedented habitat fragmentation and invasive species and all the rest, right? So the idea is what we'd like to do is define process-based models of how the real system works and actually train those against the data. So how can we do that? Well, in general, I actually think it's pretty simple to say, and the difference is it's now become possible to actually do in reality as easily as you can say it almost. So let's go back to our example before and say, well, what is a model? Well, it's a set of equations that we think describes how the world works. So in the rubber ball, it would be Newton's equations, and there'd be and so that would be the equations. And it comes with a set of parameters. There'll be these constants involved in there. In Newton's equations, it might be the gravitational constant, the elasticity on the ball, the initial velocity of the ball, this kind of thing. So you have your data, you have your model, and you have parameters. And given those two things, a model and a set of parameters, you can obviously make a set of predictions. All kinds of things. Anything you choose to that can logically follow from that set of equations and those parameters. Now, if you have some data, and I'm deliberately starting this very simple. I know if anyone's familiar with this, it will seem really noddy, but we're not going to stay there for too long. You can compare the predictions of that. So you can think of this as forward modeling. You take model and parameters and you make a prediction. And then but if you compare those predictions with data, you can obviously immediately say, well, is it any good or not? Do the predictions of the model look like the data? And at the moment, that kind of eyeballing, as we might call it in eyeballing, you can obviously do that informally. And if they don't, of course, the temptation is to change one of the two, the model and the parameters, right? So so immediately you're kind of feeding back now on the parameters or on the model structure, and you could improve either or both in principle. And the more and more you did that, you go round lots and lots of times, that's what you can think of as optimizing a model. So you're actually finding the best combination of model and parameters that you can that produces predictions that look like the real data. And obviously that's something that you could automate. So you might turn it into a bold arrow. And say now I can actually generate some routine then in the computer, let's say, so especially if I fix my model structure. And now I can try different parameter values again and again and again and find the best set of parameters that gives predictions that look just like the data. And that's what I would think of in very, very simple terms as optimizing a model. But that's not quite how the whole Bayesian thing works, not quite. It sort of is in the broadest scheme, but there's something very special about the Bayesian thing, and it's this, is that how do you actually compare the predictions and the data? If you're going to put this into some automated routine, there has to be a number here that actually measures how good the fit between the predictions and the data are, and how are you going to calculate that? Well, the likelihood-based statistics, so maximum likelihood method and Bayesian methods are a special case of that, based on the maximum likelihood. You have to have a special kind of measure here. So you can't just make something up. So it's not just necessarily an R squared, or a city block distance, or an area under the curve, whatever it might be. It has to be something called a likelihood, the likelihood. So what's the likelihood? Well, we could talk about how we write it for a start, it might help. So we write it like this, which I think makes everything clear. I don't even have to say anything now, right? But it says, this is saying the likelihood of the data given my model structure S, it's a set of equations, and a particular set of parameters which are encapsulated in this vector theta. So vector might have A, B, C in it, or gamma alpha, or whatever's relevant for the model. But the likelihood is something special. The likelihood is, and sometimes you have to be a bit careful with your language, but it's effectively a probability. It's actually saying, how probable is it that this exact set of data would arise from this model structure and those parameters? So it uses this special idea of probability. And actually in practice, we often use, it's a probability density. Okay, so that's what's a bit tricky, probability and probability density. This is the likelihood here. Now the reason that's special, I like to use this analogy of shoes falling out of the attic. So it's like when you go up into the attic and there's a bag of shoes, and you take one shoe out of the bag and it opens the bag and all the shoes come down falling onto you, right? And that's what's special about using this probability, is when you use this probability as the measure between your predictions and your data, then a lot of other things come for free. A lot of other shoes fall out of the attic, if that makes sense. So for example, you can immediately now, when you optimize, not just get a best set of parameters, but get an error bar on the parameters. So you don't just get a best alpha, but you get a 95% interval on alpha. And that's both scientifically important, because you might care about alpha, it might be something that's important to you, but also, as we'll talk about later, when we make predictions, we need to propagate parameter uncertainty through the predictions. And so it's crucial that we have a proper notion of the uncertainty in the parameters, and that effectively comes for free. It's very hard to do if you're not in this world. It's very easy to do if you are. We have the same notion with the models. So one of the very common things we want to do is choose between models. So we might want to optimize one model, and then have a different model and optimize that model and compare the two. And if we just use some arbitrary measure here, it's like, well, how much better does the second model have to be for me to reject the first one, if it's a city block distance? Whereas here, because we're in probability, we can actually do things like reject a model at 5% probability and say, actually, this model is 95% or more than 95% probable compared to the other, that kind of thing. So we get these two very special things that come for free. And the third one is that because we're using this same measure of probability, we can use the same suite of techniques to fit the model to the data. And this, for me, is really powerful, because I don't know how you felt. Different people are different. But before I discovered these techniques, I always thought statistics was like a big recipe book. It's like this rule, if this, then this. You know, if my x values are measured without error and my y values have error and the variance around the expectation looks like it's independent of x, and then oh, okay, that means I can use linear regression, ordinary least squares, linear regression. However, if I'm, then I guess and I just can't hold it all in my head, right? It was too confusing. And furthermore, every real case that I looked at didn't conform to the recipe book. There was always something about it that meant that it wasn't in any of the special cases. And then what you end up doing is changing the model or changing the data, transforming the data to make it fit into one of these predefined boxes, or actually altering the model, which is not really what you want to do. With these methods, we're almost all the time basically able to define the model we want, take the data as it is, and use the same technique every time to parameterize it. So all the stuff I mentioned earlier, like in our group, we've done more of this sort of thing than I can remember now. All sorts of things, from deforestation to the global carbon cycle to species distribution modeling to tree growth and death to whatever it might be. And all the time we're using these Bayesian methods. And you might have thought in our group that we are always talking about Bayesian statistics, but we almost never do, because we just use the same techniques. So we talk about the model, the ideas, we talk about the data and the questions, but when it comes to actually fitting the models to data, as it were, doing this stuff, basically we use the same approach every time. And so for me, it's been an incredibly enabling thing. Okay? So just broadly then, just to reinforce that, we're going to assume that we're able to take ideas in our head about how the world works and create a model S. Or several, some different ideas, these model S. Okay. And we have some data pertaining to that model X. And it's up to us, of course, now and that this model S implies a set of parameters. So other parameters. Whoa, there we go. So these three concepts again. And so the first thing is we need to be able to look at our data and say how likely would it have been to have arisen from our model. And so that's just a little skill that you build up, but it's not nearly as hard as it seems. If you've never done it, it sounds really, really tough. And we can perhaps go through, let's go through linear regression in a second, maybe. But that's not a very interesting model, but you get this kind of same. So once you've got a small set of tricks in your mind that you're familiar with doing, then it's often not very hard to write out the likelihood, which is the key thing that you need to be able to write. So the likelihood of X given S and theta. So as I said, we'll go through an example in a second. So if you can, well, what kinds of things can you do? So let's imagine you had a really simple model that just had one parameter, alpha. And this is often the sort of example you see when you talk about maximum likelihood. Then you're able to create something like this that has alpha on the x-axis, and it has this likelihood on the y. Now actually in practice, for computational reasons, we use something called the log likelihood, which is just a lowercase l and equals, no prizes for guessing, the log of the likelihood. So that's the natural log of the likelihood. It's that simple. Okay? So we use this log likelihood for various reasons, because otherwise this probability can get so low that we can't hold it in memory in the computer. So we just use the log. Don't worry about that. So we use the log likelihood. And so we can draw this, we can vary alpha and calculate the log likelihood. So we've got a set of data here, and we can try alpha, and we can say what's the log likelihood for the data given S and this particular value of alpha, like 0.1. And we can do that for different values, and we can then end up drawing a curve a bit like this. It's called a likelihood profile. And it's just the likelihood plotted against the value of alpha, given that the model S and the data X is fixed. So no surprises then in saying, well, if you're no prizes, I should have said, for saying, well, what's your best guess as to what alpha might be? Well, it's kind of this one. Yeah. That's simply the value of alpha that gives me the highest likelihood of the data X. Now, as we'll talk about just a second, actually, implicitly, you're already employing some Bayesian logic there, because remember, this thing here says how likely is the data given the model and the parameters, but we've just now made a judgment about how likely the parameter is given the model and the data. Because that's what we've really got, the model S and the data X, and we've gone and estimated the parameter alpha. And that's why this is sometimes called inverse modeling, because we've kind of gone backwards from the data through the model to get the parameters. Whereas in the forward model, we had the model and the parameters, and we went forward to get some predictions, which are a bit like the data. Does that make sense? That's why it's called inverse. So it's a bit like, the model's a bit like a lens, and you're using it the other way around. You used to use it that way around, and now you're looking at this way around. And so you put model output data in here, and you get the parameters coming out. Okay? So you've just done this switch in your mind. It's very natural to say, well, it kind of makes sense, right? The value of alpha that makes the data most likely is my most likely value of alpha given the data. You switch the two. But as we'll come across in a second, in the Bayesian world, it's not quite true, because there's a thing called the prior, which is about our previous belief that can change that. Okay? But the other thing we can do is say, well, okay, but what's this uncertainty then around alpha? We don't just want the single best value. What's the uncertainty around it? And to cut a long story short, essentially you can cut this thing at an appropriate place, like this. And if you'd like to work within the world of maximum likelihood, this thing, for most problems, you just go down a magic number 1.96 units, so don't worry too much, which gives you a 95% interval on alpha. So you come down the curve in each direction, you cut it, and that gives you your 95% interval on alpha. It's that simple. Okay? So now you've got an estimate of alpha with uncertainty, subject to your model structure S and your data X. Does that make sense? Pretty easy, right? I mean, you know, when someone explained it to me, I was like, wow, that's really easy. So if you were to do it, obviously we almost never fit a model with one parameter, to be honest. So we can up it and go, let's say you had alpha and beta. So now you've got two parameters in your model. Well, you can kind of do the same thing. You can keep playing around with alpha and beta, try all different values, and you can plot a surface here. Something like this, where each of these is a contour. Okay? And this is coming out of the board, right? You get that. So again, no prizes for saying, what in the maximum likelihood world, what's my best guess as to alpha and beta? Well, it's here, right? It's the value of alpha and beta that gives me the highest likelihood, okay? And if I want to get my uncertainty on alpha and beta, once again, I climb down this surface to some critical contour, and the critical contour might be here. And then this, I say there's a 95% probability that the combination of alpha and beta is in that region. And if I want to talk about the uncertainty in one or the other, I just drop down the lines, basically, from here. Error bar on alpha, error bar on beta. Okay. Simple as that. And this logic extends into any number of dimensions, in theory. Right? So that kind of makes sense? So before going too much further, let's maybe just work through that linear regression example. I know that it's a lot of effort to do a linear regression, which you can do with 2 clicks in Excel. But again, it's really important to remember this logic extends up to really complicated models, okay, with hundreds of parameters. So in linear regression, we say our model structure is actually like this. Well, you can write it different ways, but technically it's like this. And what this says is that each piece of data Y is drawn from a normal distribution with a mean of mx plus c and a unexplained variation of sigma. Did I make a mistake? That's good, right? I think so. So what do we mean by that? Well, we plot up a straight line here. So it's got a non-zero intercept, sorry. So we plot up a straight line. This is x, this is y. And what we say is there's a bunch of points here. So the points don't lay on the line. So people think of linear regression where the model is y equals mx plus c, but that's not true. Because otherwise the points would all be on the line. They're obviously not. So what we actually say is that there's a bell curve centered on this expected line here. And this is the normal distribution. So the mean of that bell curve is mx plus c. That's the line. And then there's a spread of points around it, which is defined by this standard deviation. And the larger that number, the more the spread. So, a linear regression is a 3-parameter problem, 3-parameter model. So now to do the likelihood, we just turn this thing around. I mean, it's extremely simple for a linear regression. And we say for a particular piece of data y, so the likelihood is we say that there's a likelihood for a particular piece of data of an observation yi, given the model structure S and given our parameters, equals, and then there are different symbols for this, but we say there's a normal density. So different people would use different notation for this. And this says, what's the probability that you would observe yi from a normal distribution with a mean of mxi plus c and a standard deviation of sigma. So your data is pairs of xy, right? x1, y1, x2, y2, x3, y3. And then there's a formula for this, and it's just, don't worry about what it is for now, okay? It's like, but there's a simple formula for this. So it just says, if it's true that it's a normal distribution centered on mx plus c, then you can look up what this value is. Now, it's actually a probability density, not a probability, but it turns out that doesn't matter for this stuff. And then finally, if you want the log likelihood, you take the log of this, but that's still for one value, and then finally you sum over everything. So the likelihood of y given s and theta equals a sum over all I of this. Does that make sense? It's that simple. So now if I give you a set of xy pairs, and I give you an m and a c and a sigma, 3 numbers, you can return something called the log likelihood that says this is how likely that combination of xy values would arise from a model with those 3 parameters, m, c, and sigma. And then once we've got that, we can do the same stuff we just talked about. So we can try lots of combinations of m, c, and sigma, and we can find the triplet that maximizes the fit, the MLE values. And those MLE values are exactly what you get out of something like Excel when you do the right click. So that's what's actually happening behind the scenes, is that that thing is actually fitting the model, and it's finding the maximum likelihood fit of that model to the data. Does that make sense when you do a linear regression? Okay. But again, because now we're in this world here, it's important to realize that it is a 3-parameter model. So there's another parameter which isn't usually reported, which is the sigma. And all 3 of them have uncertainty. And that's why you get the spreading out and all that kind of stuff, right? So that's linear regression. But most of our models are not like that. But even so, a lot of our problems actually boil down to something that's quite analogous to linear regression. So if you think about what happened, what we said was we made another way of writing it out would be to say that there's an expectation on y. That we usually do that, right? An expectation on yi, which is equal to m, which is a parameter, times xi plus c. And then separately to that, okay, we said that the observed y, so the observed y is drawn from a normal distribution around that expectation, okay, subject to a noise, sigma. So that's the other way you can write it out. You can break it apart. And it's important to realize here then that if you accepted this bit, then you can have any model up here, really. It doesn't matter how complicated it is. As long as you can create an expectation on your data, given whatever your predictors are. So in this case, y being predicted from x. But this could just as easily be MPP, predicted from temperature and precipitation. Or it could be, the lifespan of an animal predicted from its body mass, or anything at all. And you split the problem into the bit that you think you can understand in terms of the processes, and then the noise around that. Okay. So, but that's not the only way to do it. So some other problems don't fit into that package. Okay, that's how you do that. So let's imagine that you actually did have something like this, but you had a much more complicated model with 100 parameters, let's say. And let's assume you could also have a more complex noise model. So for instance, the noise on the model might depend on a whole bunch of other things. So you might have a really hideous model with loads and loads of parameters. So it's very easy to say that what you should do is try every combination and get the best fit. But you'll very quickly find, if you do some back-of-the-envelope calculations, that for interestingly sized models, it's impossible to try a decent number of combinations. So you'll never find the best fit because you don't know where it is before you begin, and it's just too much computation to find it. So what do? And that's the thing that's actually really revolutionized the way we're able to fit models to data. And that's what this tool Filzbach does, by the way, which I'm probably not going to be able to demo to you too much. I'll show you something in a second. But what we do instead is, and it is kind of a weird thing to get your head around, but you can illustrate it again with, do you remember our two-parameter problem, alpha, beta? Now, we imagine that there is a real contour behind here, like we saw before. There is some combination of alpha and beta that gives us the best fit, and there's this contour, but we don't know where it is before we begin. Okay? Well, we have a technique, and it's called Metropolis, Hastings, Markov chain, Monte Carlo. So it's a lot of letters, MH, MC, MC. But it's really simple. The reason it's a Markov chain is because it sits at any one time at a particular position in space. So it's defined by a combination of these. So in this case, alpha and beta, if it's a two-parameter problem. And then from then, that's all you need is that to determine where it goes next. So it makes it a Markov chain. And so what it does, it sits somewhere and it looks at the likelihood here. So you pick somewhere randomly to begin and it says, what's the likelihood? And then you propose a new place, say over here. And it looks at the likelihood again and it says, what's the likelihood there? Now, no surprise, if the likelihood's better, it accepts that move. Okay, that's the really obvious bit. And so it tends to climb uphill. And if you keep doing that enough, obviously it has a tendency to climb to the top of the hill. But if it picks the likelihood that's worse, and this is the weird thing, it doesn't reject it. That it accepts it, it might accept it or it might not. It flips a coin. And it makes a probabilistic decision about whether it accepts or rejects that move. And it does that based on how much worse the likelihood is of a new place. Now that has two important effects. One of them is that it means that it doesn't get stuck so often in local maxima, as they're called. So I want you to imagine that there's a place here that's quite good, but it's not as good as here, which is actually the best place to be, okay? If you only ever climbed uphill, it might climb up here and get stuck. Whereas this thing, because it sometimes comes downhill, it sometimes comes down and makes it onto the higher mountain top. Okay? So that's kind of the easy bit. So you know, and to cut a long story very short, the point is now that this thing is very blind. It can be applied to any model, but it's very, very good at finding a good set of parameters. And this can work efficiently for a very high dimensional space. It's quite weird because it's not 2D. It might be 15D. And yet it's able to navigate through that 15-dimensional space to find the best set. But actually, that's not really why this particular algorithm is designed that way. It's designed actually to do something incredibly magical. So to illustrate that, if you can see this, let's go back to imagine that we did just have a one-parameter problem, like a parameter A. So for a one-parameter problem, that the algorithm is just hopping back and forth, right, on a line. That's all it can do. So it's only got one dimension, the poor thing, that it can actually navigate in. So you'd start somewhere here, and it would maybe move this way, maybe sit there for a bit, maybe move back, maybe move forward, and it would. And if you watched it long enough, it would go bam, 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 like this, and it would go back and forth and back and forth. And importantly, it never settles down. It never freezes on the best set, because there's always some probability it's going to come back downhill, right? So it never settles down. It just goes back and forth. So it's like, so what? Well, if you actually break up this axis now into chunks, and you say, what fraction of the time did it spend in each of those chunks? You'll find, you plot that as a bar chart, let's say. You'll find something like this. And you find something really amazing, which is that bar chart exactly follows the underlying likelihood surface. And it might take a while for that to sink in, why that's so magical. But let's look back at that 2D case again. So if it was in 2D, in alpha and beta now, this chain comes in from the cold. And then it starts moving around like this. And that's the bit I can actually show you. So get away from me and the board. So the thing is moving around. And so we have a little, so we're almost done with this session. So I'm not going to actually take you through tutorials about how to use Filzbach today. But this is what Filzbach does behind the scenes. But you can use Filzbach from C++, from R, and you can also use it inside the thing that we're going to use this afternoon called Distribution Modeler. And you can use it from MATLAB as well. So just get in touch if you want to use those things. But if we do, we'll search for me again. So remember then that this thing is wandering around in this multi-dimensional space, and it never settles down. So let's have a look down here. Thing's just going to spin open for a second. So it goes wandering around and around. It never settles down, but it distributes its time here in proportion to this likelihood surface. Okay. And so what it means is that if we allow what's called a burn-in, so there's a phase here where it's coming in from the cold, it's finding the right place to be. Okay? And so we let that happen, and we wait until it seems to have sort of settled down, not frozen, but sort of settled down where it's distributing its time. And once it has settled down, we say, well, if we want the best guess, basically, at our parameters here, we can just look at the average of where it spent its time. To average all the alpha positions, and that's called as the posterior mean. And for a problem with non-informative priors and plenty of data, that's going to be our MLE value. And similarly, if we want to do the 95% interval around that mean, we find the region within which the chain spent 95% of its time. And if we want to know what the correlation between these parameters is, because we often have a correlated space here, we can just look at the correlation in these samples. We just treat them like anything else and look at a correlation. So all that stuff just comes flowing out for free. And again, I'd remind you, it works efficiently on really large problems. Now, it does still require quite a bit of computation, and which is why it's only reached prominence in environmental science recently. But let me just give you a quick example. We have, for example, if we do the linear regression, you can read about the model there, and you can see the code that would run that in C++ here. And then we can have a look at some of the data here. So obviously we've got points that have come from that model, so we just generated those points artificially. But now we can start the sampling, and when we do this we're going to start somewhere random, and then the thing is going to move around, right? And so we can see that here. You know what? It's too fast. I think we ought to pick a slower one, like this one. That was too fast to see. So here we go. So here it is moving around, and this is the burn-in. It's coming in from the cold. Okay, and it's finding that it's better off down here. So the likelihood here is so bad that it sort of propels the chain this way. But after a while, it starts to settle down into this sort of banana-y shape. And you can see that although the chain itself is moving around all the time, the shape of those samples is kind of stabilizing. And that's our sample then from this posterior. So if we want to know what this is M0 here, what the Bayesian mean on that thing is, the posterior mean, we can take the center of gravity of this cloud. It's about here. And similarly for this parameter. And if we want to know the spread, we can do that spread in either direction. Okay, that's the idea. So that's Filzbach in a nutshell. And so let me I could do a couple more concepts, or I could do the stuff here. I think what I'll do is I'll do the concepts because we're about to break, and when we come back, we're actually going to be fitting models using Filzbach anyway in Distribution Modeler. So we may as well leave it until then, some of the details about how you can use Filzbach. So I will finish on time, by the way, at 4. I would never take anyone away from their tea. Or is it coffee here, I guess, for you guys? So, okay, so what's left to say? Well, what I like, actually, is the fact that, to be perfectly honest, I don't think there is that much more to say about the overall idea about this approach to fitting models to data. And just to backtrack, can you see what I mean by the idea that we can, in principle, fit any model now to data? Because as long as we can write the likelihood, as long as we can say, you give me a set of data, and I can say, given my model S, and for a particular set of parameters, as long as I can generate that log likelihood, then that is enough to set that thing running. And then I'm going to get my estimates of my parameters. No matter how complicated the model is, in principle, it's going to work fine. And it works for really horrible models now, so you don't have to worry. So what's missing? Well, the main thing that is missing is that so far we haven't really been in what most people would think of as a Bayesian world. And the reason is that really what we should be using, and what we have been using, is the idea of a posterior probability density, not a likelihood surface. And the difference is the posterior, this is the actual probability. We didn't use that P yet. The probability that the data would arise from a particular model structure thing here is proportional to the likelihood, but it also needs to be multiplied by this, which is the probability of the parameters in the first place. Now this this probably could be conditional on S, to be honest, but that's a bit pedantic. But the idea is that given our model S, you could actually have a guess ahead of time about what the parameters are likely to be. And the more ideas rich your model, the more you're going to have an idea about what the parameters are. So if we've got something like the maximum growth rate of a tree, let's say in millimeters per year, I can tell you that something like 10 is what you're looking at. And if you're talking about the maximum height of an Amazon tree, you know it should be about 40 meters and so on. You've got an idea about what they are. And that's what this thing is. So this is called a prior, and it says, if this is my parameter alpha, and this is my prior on alpha, then I can actually have some prior belief here in my problem. Now, if I say I don't have any prior belief, I'm ignorant, then I represent that by making this a straight line. And what it says is, I think for a height of an Amazon tree, 1 centimeter is just as likely as 1 kilometer, okay? Obviously, it's not true, right? But I could do that if I want to. And if I do that, notice then that the likelihood only if I compare two different parameter sets, which is all, remember, that's all that drives the chain, the Metropolis thing. All it does is compare. This thing won't be any different because it's flat. When it proposes a different alpha, it will get this. So I can ignore this, and I can just run it on here. And that's why a likelihood analysis, we think of, is really working on a posterior with what's called a non-informative prior. And then just in the last minute or two, I'll just say, so what happens if you do put an informative prior in? Well, it's very simple. Is that you can now draw two things. I can draw my likelihood profile surface, which might be like this, and I've got my prior belief, which might be, say, like this. So this is what I believed beforehand. This is what's in my brain. This is what the data says. And what's going to happen is the chain, that chain, the Metropolis algorithm, is going to compromise between these two. And it's going to give me some hybrid, which is going to have a mean in between the two. So something like this, right? So it's going to balance between what we thought was true ahead of time and what the data seems to be telling us. Now, if we have huge amounts of data, this will be much stronger than this, and we'll simply get what the data says. So it doesn't matter what we believe if we've got huge amounts of data. Our beliefs get swamped by the data. If we have tiny amounts of data, then all we're going to get back out is what we expected in the first place, the prior. But a lot of the time, we're somewhere in between. We do have some previous expectations and some belief on the one hand, and we've got some data, but not enough on the other. And the Bayesian thing very, very naturally averages between those, okay? And that, honestly, is basically the difference between a Bayesian approach and a maximum likelihood approach. And what's funny is that they're often, I don't know how many people are familiar with these ideas at all, but they're often presented as if they're two very different worlds. Like, oh, you know, you're a frequentist and you're a Bayesian, or you use different tools. Right? MCMC is a Bayesian tool. right? And maximum likelihood, you use simulated annealing, apparently, with a likelihood profile, et cetera, et cetera. But really, to be honest, I don't think it's a useful distinction for a lot of people. Really, you should just think, if I put a prior in, it's Bayesian. But basically, the concepts are really, really similar. And for complex models, a lot of the machinery that's traditionally used in maximum likelihood is not efficient enough to fit them anyway. So you end up using the MCMC machinery, which is more traditionally associated with the Bayesian analysis. Okay. Now, just in the last minute, there are a few other topics that do come up in this kind of work. So I guess I'll just list them really, really quickly. We'll come back to them after the break anyway. So one is when we go to make our predictions, and this for me, this was the single piece of magic that meant that I just dropped all other forms of stats and so on, was what if you want to make a prediction and put the parameter uncertainty through the prediction? Well, you know, we've got a set of samples here, right, from the posterior distribution. So if I can afford to run my model 100 times, all I need to do is pick 100 of those at random and run the model 100 times with those different parameter sets. And the output that I get is going to be an unbiased estimate of the uncertainty on the model predictions. It's incredibly easy to do. So again, this could be a hideously difficult model. But if I can run that Metropolis Hastings chain on the thing, I get a set of samples of the parameters, I choose so many of them, run the model, and boom, out I get. It can be anything. So it could be the potential response. For instance, if you want to know what's the probability that the Amazon rainforest would collapse under climate change, in principle, if we've got a decent model and enough data, we run this on it, the answer is, well, for some of those parameter sets, it collapses, and for some of them, it doesn't. And if we choose 100 at random and it collapses for 15, the answer is 15%, kind of. So just a couple of other issues. So one is, we often want to choose between models, as I mentioned. Long story short, there are ways to do that. Okay? There are rational ways to say, if I run this entire analysis for several different models, then I can make an appropriate choice between them. And there's a thing called hierarchical Bayesian analysis that comes up. Okay? And again, I won't go through that, but it's not very difficult in practice. It's actually really easy and it's a very simple extension of this, basically, this idea that, and I think with that, because it is, according to my watch, 4:01, we will stop. So that was the lecture style bit. Thanks for that. And again, thanks very much for being up for trying FetchClimate. And I'm sorry we hit a few brick walls there. Nonetheless, I'm going to throw myself open to falling on my face again. So when we come back after the break, we're going to try and get hands-on with a tool that enables us to specify models and run MCMC chains on them and make predictions. And we're even going to try and push those predictions into FetchClimate. And we'll find out how foolhardy that idea is after the break. So enjoy your break. Thanks.